Alright, so here we are with continuing with 12-2, talking about chords and arcs. There's two more theorems that I want to discuss today, and then followed by a few examples. So let's get right to it. So the first theorem says, in a circle, a diameter that is perpendicular to a chord bisects the chord and its arcs. So a diameter that is perpendicular to a chord bisects the chord and its arc. So I have pictured our given information. So first of all, we know it's a circle, right? So we know it's a circle, that's given. We know we have a diameter, so in that case it would be, the diameter would be AB, right? I don't know why that writing was so large right there. The diameter would be AB, so that is, not AB, EB, I apologize. Diameter is EB. And we know that that the diameter is perpendicular, right? The diameter is perpendicular to the chord. So that's listed here. So that's all the information that we know. Now the conclusion then is that it bisects the chord and its arcs. So what can we say? We can say that it cuts this chord AC, right? It cuts the chord AC in half. It bisects it, which means that AD is congruent to CD, right? So we know that this segment length is congruent to this segment length. They have the same length since it is bisected. We also know that arc AB is congruent to arc CB. Again, because it bisects this entire arc here, or it cuts it in half, so this arc would be the same length as this arc here. So that's kind of what that's saying. If we have a diameter that's perpendicular to a chord, then it bisects the chord, and it bisects the arc that it forms. Okay? That one's pretty straightforward, so let's go to this next one. This one will have an example attached to it. In a circle, a diameter that bisects a chord is perpendicular to the chord. So there is an exception, we'll talk about in a second. Let's look at the given information. We have a circle, we have a diameter, again in this case that's AB. It bisects the chord. So that's all that's given to us. So we know that diameter AB here bisects CD, giving us these two congruent parts. Now, what the conclusion then would be is that we can then conclude it is perpendicular to the chord. So the theorem is saying that we can now conclude that it's perpendicular to the chord. So I will write our conclusion here would be that AB is perpendicular to CD. Okay. Now there is an exception to this, and if you want to think about it for a second, pause and think about it, you may. You want to think, is there a chord that when a diameter bisects that chord, that it is not perpendicular? Well, here's kind of how to think about that. Let's think about all the chords that we could draw here. Right? There's a chord here, there's a chord here. There's so many different chords we can draw, right? And I'm intentionally drawing it to where it's not perpendicular anymore. Now this chord, the one that I just drew, is bisected. I'll draw it one more time. So I'll draw it in blue here. This chord here does get bisected, but it should be going directly through the center. It does get bisected because, you know, it's a diameter, right? And it's cut into two congruent pieces like so. But it's not perpendicular. This is clearly an acute angle. This is clearly an obtuse angle, so they're not perpendicular. So the exception is if the original chord that we're discussing is also a diameter. So the exception to the rule is that if a diameter is bisecting another diameter, it does not necessarily have to be perpendicular. It could be, if you have a quick sketch here, one diameter, another diameter, it could be perpendicular, but it does not have to be perpendicular. Okay, so that's kind of where that's going there. Now, let's look at an example. So they're giving you that this segment here is 3, that this segment here is 4, and this segment here is also 4. So we know that this diameter here is bisecting this chord because, again, it cuts into 2 congruent pieces, right? So we know it bisects the chord, which means it must be perpendicular. So we can just solve for x and say that x is 90 degrees. X is 90 degrees. Now, if we're looking at how to solve for y, well, that's a little bit more interesting, you could say. Because, again, y is just this tiny segment here. It's not the entire thing, right? It's just, I'll draw it in red here. Y is just this part here. Okay? So we're trying to solve for that. Well, here's the strategy for a problem like this. If you can find the radius, then that radius in pink here would be congruent to this radius here, which is what we want because we know this part of it up here is 3, and then we could find the rest of it. So that's kind of the strategy. So we need to figure out how to find that pink radius there. And this should be pretty straightforward. We have a right triangle. We're able to conclude that it's a right angle, which means one of my leg lengths is 3, the other leg length is 4. Now my hypotenuse would have to be 5, right? Because, you know, it's a 3, 4, 5 right triangle. If you wanted to solve for it, you would have done Pythagorean theorem to solve for, let's say that value was c, or let's make it more realistic and say it was r, and you would have solved and gotten that r is 5. So what does that mean? Well, it means that this, I'll do it in green here, this segment here is also 5, but we already have part of it that is 3, so the other part must be 2. So we could say that 3 plus y equals 5, right? Because we have 3 here, we have y here. They add up to a radius, which again we know is 5. So we then say that y equals 2. And whatever units it is, meters or whatever it is. Okay, so x is 90 because the diameter bisects the chord. It must be perpendicular. We use that information to set up the Pythagorean theorem, find a radius, and then look at the relationship from there. Okay, so that's kind of the strategy there. There's going to be a lot of problems where you need to think to draw in your own radius as we did here, because that radius was not originally pictured. So you need to always keep that in mind. Sometimes you can draw your own radius, and that's okay. So let's look at another example here. We know that well, first of all, we're solving for x, right? We're solving for x, and we are looking at a picture where we have a chord here with a line that's perpendicular to it, and we also have a radius somewhere over here. Okay, so here's again the strategy. We have a radius up here, which means we need to solve for the radius, right? We need to solve for the radius. Well, we're going to use a theorem. Let me just look for it real quick. This one. A diameter that is perpendicular to a chord bisects the chord and its arcs, right? A diameter that's perpendicular to a chord bisects the chord and its arcs. So if I drew my diameter here, right? That was really poorly drawn. Let me try that again. If I drew my diameter here, there we go. We know it's perpendicular to the chord, which means it must bisect the chord and its arcs. So do I have to draw that diameter in there? No, because we're looking at just a segment of that diameter right here, right? It goes through the center. It's perpendicular to that chord. So you could just extend it to create the diameter, but we know that this bisects this chord, which means each of these segments must be 11, right? Because that's just half of 22. So if each of those segments are 11, then what I can do is I can then again, this is always your strategy here, I'm solving for a radius, so I need to draw in my own radius here, creating again a right triangle where I know that it's 6 squared plus 11 squared equals r squared, or in this case it would be x squared because x is the radius. So when solving this, we have 6 squared, which is 36, plus 11 squared, 121, equals x squared. 121 plus 36 is 157 equals x squared. So you would then say that x equals rad 157. So this is not a Pythagorean triple, but nonetheless we can still solve for what x is. I don't think this can be simplified, which means you just leave it as rad 157. Okay? Let's look at another one. This is the last one. Should be able to fit it in the next 4 minutes or so. So here's the picture down here that I want you to focus on. So that's not a box that it's supposed to be. So we're looking at this picture here. It says circle A and circle B are congruent, and that CD is a chord of both circles. So it's kind of a cool concept, right? We have a chord that's on both circles, and the circles overlap. So we know that AB, it's this segment here, we know that segment is 8. We're looking at question 30. We know that segment is 8, and we also know that CD, which is this segment here, is 6. Alright, we know that segment is 6. And we're looking for how long is the radius of either circle. So we're trying to solve for the radius. Now, how I drew the radius there is not an ideal spot to draw it. Again, you want to always try to come up with a triangle, right? You want to come up with a triangle. Okay, so that's always the concept there, is to try to draw the radius to come up with a triangle, because then you can start using things like Pythagorean theorem, right? Now we first want to look to see, is this a right triangle? Okay, is this a right triangle? So we have to think about this here. If I were to draw another radius there, right, we should be able to conclude that this is an isosceles triangle. So this black triangle that I drew here is isosceles, again, because this is a radius and this is a radius, right? Now, since it's isosceles, we can then also say that the base angles are the same, right? The base angles are the same. So we have this, it's congruent to this. Okay? Now, we also know that the this leg is a shared leg, right? So we have that leg is there twice. And then we can say that this length here is congruent to, where is it? Hold on, let me write it for you. This length here is congruent to this length here. And that has to do, I'm not going to go into extreme details of it. We can say this length here, right, is a radius. It's congruent to this length here, that's also a radius. And you can cut off this shared part here, which will then lead to them being the same. So that may have confused you a little bit. I realize that explanation was not amazing, so I'm going to, I'll secede one there. However, the concept is still good. Okay, we know we have the radius here. This is going to be a right angle, which means what? We have a segment that cuts the chord in half. It bisects the chord, right? So if this whole chord is 6, then we can say that each part of the chord is 3. And if each part of the chord is 3 there, I also know that this green segment, or this part, is congruent to this part, which means we have 4 and 4. And again, we have a 3, 4, 5 triangle, which means the radius here is 5. Okay, so that's the concept. You're creating right triangles within a picture. You're drawing a radius to create a right triangle, and you're going from there. I encourage you to try 31 and 32 on your own. 31, you can check the answer in the back of the book as well. So, all right, guys. Well, that's it. There shouldn't be anything left there. So, with that, have a splendid day.